So broadly discuss this initially. So our topic is nuclear shell model. But before we start with nuclear shell model, you can write this down as a heading if you're making your notes. Okay, we have to know the basics. That's important. And the basics comes from the electron shell model. Okay. Basics is from electron shell. So electron shell model, when we studied it, probably it was in undergrad, it was there, or maybe in MSc also, atomic and molecular physics, it will be there. This is also a very important part of chemistry syllabus. So even if you study chemistry in your undergrad, it might be there, and so on. Okay. So what do we exactly mean by shells? So when we talk about the Bohr model, okay, if all of you remember, a lot of things was actually explained by Bohr model. It's not that Bohr model was a total failure. But what it usually said was that we have the nuclei and so we have the nuclei and we have this electron which is actually revolving around the nuclei. Okay, so that's important. So if that happens in a way, we can say that just a moment. Okay. So if that happens, that we basically have the electrons revolving around the nuclei. We have the electrons revolving around the nuclei. There are certain orbits in which it's going to move around. Okay, it's going to move around in certain orbits, and the number of electrons that we have is restricted for a particular orbit. Okay, so these are basic ideas of Bohr model, and of course there are a lot of postulates. But moving ahead, we have to talk about shell model. It means that the electrons that we basically have are residing inside shells. Okay, they are residing inside shells, and if you remember, there are a number of shells that are being explained. Even if you study about X-ray diffraction and all, you study about these shells, K, L, M, N. Okay, these are actually called the shells. Okay, so these all are nothing but shells. Okay, which we know, and we have these the electrons residing inside these shells. And if you remember, we can actually denote them with a number because it's quantum mechanics and it is discrete. It's not that you have a continuous shell. It's number of shells that we're talking about. So if we represent it as 1, that is the first shell, 2 is the second shell, 3 is the third shell or M shell, 4 is the fourth shell or N shell, and so on. So these are nothing but numbers which is actually written as N, and this N is something which we usually call it as principal quantum number. So this is something which you already know. It is principal quantum. Now, it's not that you have the electrons inside a shell. Even inside a shell, there will be certain thing which is actually called a subshell. Okay, so a subshell might be S, P, D, F, and so on. Okay, so these are nothing but subshells. So that means inside a shell, there will be subshells. So there will be subshells inside K shell. Okay, or let's write down the subshell. Okay, inside K there will be subshells. Inside L there will be subshells, and so on. So it will be subshells. Now the thing is, how many subshells will be there inside K and so on. So these shells or subshells, whatever we are saying, is an imaginary concept. Okay, we know that it's going to reside in that particular location, and that location is going to state what is going to reside inside that location. The electrons. Okay, the electrons will reside inside these shells and subshells. Okay, the electrons will reside inside shells and subshells. So these shells and subshells are the locations. Okay, the regions. So it's not that there is a definite shape to this. There is a definite shape for its existence, but it's not that there is something some location which is actually bounded. Okay, because it's basically based on the idea of probability. So these are actually called subshells. Okay, so if it is an S subshell, we usually write it start with 0. Okay, and then it's 1, 2, 3, and so on. Okay, so this is basically, mostly denoted with L, and this is called the azimuthal quantum number, if you remember. Azimuthal quantum. So this is the idea of shell and subshell. Okay, so if I basically have the first shell, okay, I'll write it down like this. This is the second one, KL, this is M. Pardon my drawing skills, but I hope you're getting the concept here. Okay, so this is K, this is L, this is M, this is N, right? So this is represented as 1, this is 2, 3, this is 4. And if you're talking about subshells, that means in K, there will be only one subshell. There will be only S subshell. It can be there, there will be P, D, and F, but there are no electrons beyond S. Okay, there can be a maximum number of 2 electrons in this shell. So that means even if there are higher subshells, there won't be any electrons there. So it is quite meaningless to consider that P, D, F subshells will be there. Okay, in L there will be 2. Okay, you can have maximum number of electrons, and it can be accommodated by S and P itself. In the third one, it will be 3 SPD. Okay, and the fourth one, N shell, it will be S, P, D, F. Okay, so in this way, usually the shells and the subshells are designed. Okay, so the question is how many electrons a subshell can have. Okay, that is also a very important idea that we should have. Okay, so maybe let me write down this, and all of you please make a note of these things, because these things are important as we proceed with the nuclear shell model. So when we say a subshell, okay, we can say a subshell. It basically can have, there are derivations for this, but we're not going to go into that right now. It can basically have 2 into 2L plus 1 number of electrons. Okay, this is the maximum number of electrons that a subshell can have. Or in general, we can say if these many electrons are there in that shell or subshell, it's full or it's filled. So if I talk about, the S subshell, you can simply say how many electrons will be there. 2 into 2 into L. L is 0 because this value is 0 for S subshell plus 1. Please remember these and recall these things. So that means there can be maximum of 2 electrons, right? 2 into 0, 1, so it's there. Similarly for P subshell, you can actually have it as 2 into 2 into 1 plus 1. So that will be nothing but 2 into 1, 2 plus 1, 3, 3 into 2, 6. SPD. You should remember these, very important. But even if you don't remember how many electrons will be there, remember the formula, and then you can easily write it down. So this will be for D shell, 2 into 2 plus 1, which is equal to 4 plus 1, 5 into 2, which is equal to 10. Okay, and let me just write down for the next shell as well. Okay, so you can remember. We are going to use this as well in the nuclear shell structure. So it is 2 SPDF. So F is 3 plus 1. So it is 2 into 3, 6 plus 1, 7 into 2, 4. So and so on. Okay, S, P, D, F, G, and so on. So you have to remember these numbers. That is also very important when you talk about shell structure. Okay. Now there is a very important, set of elements which we basically call as inert. Okay, inert. So let's take some examples. Maybe we're just talking about atoms right now. We are not into the nucleus of now. And we have this idea of what is we call as the inert gas. Now, what is inert gas? Okay, it's going to be non-reactive with the external environment. Okay, these are very stable. Okay, you cannot easily reduce or oxidize that element. Okay, that's again there. So these are all chemical behavior that we have, and we have got example of neon where the number of protons is nothing but equal to 10. Okay, so its behavior is kind of different from its neighboring element because it is inert, and it is inert because there is a fixed number of protons there. Okay, the number of protons or the number of electrons plays a very important role in deciding whether a gas is inert or not, whether it will be reactive or not, and so on. Okay, we have got argon. Okay, and for argon we can say Z is equal to 18. Okay, these elements you have to recall and remember, that's important. If you go towards a higher number of protons, Krypton maybe Z is equal to 36. There are of course isotopes of these which are also quite stable. Okay, and then we have got xenon. Okay, and for xenon Z is equal to 54. Okay, and we have got radon Rn, and for this Z is equal to 86. Okay, so what is so special about these elements, okay, or these systems? Okay, so what happens is in these the electrons that we have, okay, please make a note of this because this is the same concept that we are going to carry forward in nuclear system. The electrons that we have are very much tightly bound, so it's not that you can easily break out that electron. Okay, or in simple words we can say that the ionization energy is high. Ionization energy, I hope you remember, you have an electron here, and if you want to knock out this electron you have to give some energy. Okay, how much energy you need to knock out that electron is the ionization energy for that particular element. Okay, so the ionization energy is very high. That means in simple words the electrons are tightly bound. If the electrons are tightly bound, that means they cannot react with an external environment. As a result, they are very much inert. Okay, so we can say the first ionization potential is high. Okay, so make a note of these. Ionization potential is high, very high. Okay, so this is a speciality of these kind of elements. Now the question is, does a similar thing also exist for the nuclei? Okay, now we have seen in the previous classes that we can actually draw a graph. Okay, if you remember, we can actually draw a graph. I don't have the diagram right now. I can show it to you roughly. We can draw a graph between A or mass number, okay, and on the y-axis we can actually have binding energy for nucleon. And when we do it, okay, we have seen this in case of fission and fusion as well. We can see that there will be certain peaks which will be observed for certain elements, okay, and then there will be some rise, and then there will be a drop. So there are certain peaks which are also there. Okay, let me just import a diagram and show it to you. Okay, just give me a moment. Let me just. So this is an image which I actually got from the net just now, and you can check this. Okay, maybe we can expand this a bit. Okay, and if you do it, okay, you check this values here. You've got the mass number along the x-axis, and you've got the binding energy per nucleon along the y-axis. And as I've seen in the last, I think last time also we discussed this, that iron, nickel, these are very stable, and this will lie somewhere here. That means their binding energy is maximum. It will be somewhere near 8. Okay, you can check this, and you can see that this will be somewhere near here. Okay, you can check it's near 8. Now, on the other hand, if you check for other nuclei, for example, uranium goes towards the end, the binding energy reduces. Okay, and it gives rise to fission, fusion, and so on. But we're not going to discuss that. But you can check certain elements here. For example, lithium, or maybe helium, or carbon, okay, oxygen, nitrogen. They are actually having more binding energy compared to their neighbors. Now, in simple words, what exactly it means that when we have more binding energy means that the system is more or less more stable than its neighbors. Okay, so if it is more stable, that means we are tightly bound. The nucleons, the neutrons, and the protons are tightly bound. Just now we have discussed that even if you are considering an electron, they are also tightly bound in case of inert gases. So that means these two ideas are more or less complementary with respect to each other. But what we have seen above is that it's not that for every gas or every element it is going to be inert. No, it is going to be inert depending on a particular number of protons. The proton is 10, 18, 36, 54, 86. That means the number of electron. Okay, it is not getting reacted because the outermost shell is full. That means the number of electrons are 10, 18, 36, 54, 86, okay, and so on. Similarly, in case of nucleon also, it means that there will be a fixed number of protons, let's say, okay, and a fixed number of neutrons. based on which we can actually say that the nuclei will be more stable. That means nuclei with these numbers of protons and neutrons are going to have higher binding energy. Okay, so what are these numbers? It has been observed, okay, experimentally as well. Or if you can look into these elements here, only few number of elements are listed. We can actually list more elements later. But then, protons, if it is 2, 8, 20, 28. Okay, these numbers are something which you should actually remember: 50 and 82. You cannot go beyond 82 because the next magic number is quite high, and any element with that much magic number of proton does not exist. Okay. Similarly, for neutrons also we can have 2, 8, 20, 28, 50, 82, and 126, because there are elements which has got 126 number of neutrons, but there are no elements which 126 number of protons. So if any element has got the number of protons or neutrons corresponding to these numbers, or both of them correspond to these numbers, they are actually called magic numbers. Okay, these numbers are actually called the magic numbers. Okay, so you have to remember these, okay, because this is very important in shell model. Magic numbers are something which are actually explained by shell model. So this is magic numbers. Okay, so what are magic numbers? If someone asks you, or you can actually write it down also. So magic numbers are analogous to atomic number of inert gases. Okay, so you can see this, and at these numbers, the nucleus is going to show exceptional stability. That means their binding energy is going to be more. Please remember these concepts, because these are important conceptual questions. Okay, analogous are, sorry, are analogous to atomic number of inert gases. Analogous to atomic number of inert gases, because if the atomic number is such as 10 and as we have seen above, okay, 10, 54 and all, they are inert. Similarly, when we are talking about protons and neutrons, if the number is such, these numbers, that means they are going to be very stable. So they are more or less complementing each other. Okay, so there is a category for this as well, N and Z. If the number of protons or neutrons is equal to 40, okay, this also comes under semi-magic number. This is semi-magic number. That means it is not going to show more stability compared to the numbers which have number of protons and neutrons as magic numbers. Okay, the elements which have got number of protons and neutrons as magic numbers, but it is also going to show more stability compared to its neighborhood. It's not very high, but it is still better than its neighbor. Okay, so this is actually called semi-magic number. So if you have an element where we have got number of protons and neutrons as 40, that is semi-magic number. There are certain elements where we have the number of protons as well as number of neutrons both lying in the magic number category. So these are called doubly magic numbers. Okay. So as I said, that there will be certain elements which will actually have both the numbers of protons and neutrons belonging to these values. So they are actually called doubly magic number. They are actually going to show you exceptional stability. Okay. So here what we can write it down as doubly magic numbers. Okay, I'm going to give you some examples of these elements, but we are going to show except highly exceptional stability. Okay, you can say they are going to show highly exceptional stability. They are going to be more stable compared to element which has got only either proton or neutron as belonging to the magic numbers. But if you're considering an element like, let's say, helium, okay, we know that the number of proton is 2, but at the same time number of neutron is also equal to 2, and both of them belong to the magic number. So that means this is going to show exception in stability. We can talk about a lot of elements like that. For example, oxygen, where we have got Z is equal to 8, neutron is also equal to 8. Okay, we need to know these elements. Okay, if someone asks you, that's important. We can talk about 40 calcium, where Z is equal to 20, and number of neutron is also equal to 20. Does it mean that both neutron and proton should be same if they are under the category of W magic number? The answer is no, because if you consider something like 48 calcium, okay, Z is equal to 20 again, but here we have got the number of neutrons as 28. So, 20 is a magic number, 28 is also a magic number. So it's basically belonging to the W magic number category. Okay. Apart from that, lead, as we know, we have said in the radioactivity also that lead is very stable. It is actually nothing but, if you're talking about uranium, actinium, or thorium, when they want to become stable, they will finally be equal to lead. Okay. So lead 208, Z is equal to 82, which is magic number, the maximum number that you can have. Okay. It's a heavy element, no doubt, and n would be equal to 126. So 126 example would be lead. So this final two values, 82 and 126, you can take the example of lead. That's important. But we have seen that lead is not only having 208, it is also having two isotopes more, 206 and of course 207. So what does it tell me? It tells me that if an element belongs to a category where we have magic numbers involved in numbers of proton and number of neutrons, it's going to be very stable, and at the same time it's going to have isotopes which are stable as well. Okay, so the isotopes of such element will also be stable. So this is what is important in magic numbers. Okay, so these things that we're talking about, magic numbers and all, is actually explained by shell model. We have to have a theoretical model for this. So that is nothing but the shell model. So what we're going to do now is maybe imagine, okay. So now what we're going to look into is the nuclear shell model. But before we look into the nuclear shell model, you actually all know about the energy level diagram that you can actually see in the screen. Okay. But let me not go into that directly. Before that, let me just tell you something about potential well. Okay, I hope all of you remember in quantum mechanics we actually have done this. Okay, this is a very important concept that we should all know. Okay, in quantum mechanics also you have done about it. Okay, and this is something which is called as the potential well. So what do you exactly mean by potential well? It means that if you're basically having an electron revolving around the nucleus, it cannot escape the gravitation or I mean the Coulombic force of the nuclei, as a result of which it actually stays bound within the system. If something is bound, that means we can actually compare it with a particle being trapped inside a well. Okay, so we can say that this is a well, and maybe I can say the width of the well is A. Okay, and inside this the particle is getting trapped. Okay, so if outside the potential is infinity, that means it cannot escape, and inside it is zero. This is actually an example of infinite square well potential. Now the question is, if we do such things in case of an electron, even if you're taking out a finite square well potential, we can actually find out the energy of the electrons, okay, which is bound by this potential. And if you remember, you might have derived it in your quantum mechanics as square well potential. It is n square h cross square divided by 2m a square, where a is the width of the potential, right? So this is the relation that we have, and I hope you know that this n will actually correspond to the value of 1, 2, and so on. So this n is actually related with something which we call as the principal quantum number. So this is what happens in case of electrons. The question is, if we are basically having a nuclei and we are having a neutron and a proton trapped inside the nuclei, can we use a similar concept? The answer is yes. There will be again a potential well for these as well. That means the protons and the neutrons can also be compared with an electron trapped. Okay, so these are actually trapped inside the nuclei. So that means they can also be represented in terms of the potential. Now, what kind of potential do we have? We have studied so many types of potential. What potential will be perfect, which will actually explain the electrons and the proton inside the nuclei. Okay, so we can talk about the square wave potential, which you might have studied. We can talk about the harmonic oscillator problem or harmonic potential. That is also something which you might have studied in your, uh, you know, quantum mechanics. But square wave potential, if we talk about this, and we are actually going to find out the energy value, we will see that this does not explain magic numbers. Okay, what do you mean by these energy levels? It energy level shows and tells me that how many electrons will be in this level, how many electrons will be in this level, and so on. But if you can take out the square wave potential and find out the energy from there, we're going to see that this does not explain the concept of magic numbers. That means if you have electrons here, electrons here, electrons here, and so on, all of them won't add up and show that the stability state will be achieved. We will have magic numbers. Similarly, for harmonic oscillator problem also, we are not going to observe that. We are going to draw some diagrams on that and going to understand it better. But then there was a potential which actually explained a lot about it. Okay, this is called Wood-Saxon potential. Wood-Saxon potential. The problem was, even with Wood-Saxon potential, we can actually observe these. Okay, we can take a note of the diagram right now. This idea that we have, this diagram that we have, is actually based on Wood-Saxon potential, energy level diagram. Okay, but then this is also not explaining magic numbers. So what happened is another concept was used, that Wood-Saxon potential was taken plus the concept of LS coupling or coupling. Okay, if you remember LS coupling. So the spin orbital interaction was considered, and that actually explained all the magic numbers. So in the next few classes, what we are going to understand is how these potentials does not explain the magic numbers, but Wood-Saxon potential along with the spin orbit interaction is going to explain the magic number concept. Okay, so we have understood magic number. Now we have to understand what does it, which one explains it. Okay, so the potential which explains, okay, maybe I can make this note. This is important. Before we start, we should know what are we aiming for. Potential that explains magic numbers is Wood-Saxon potential plus spin orbit interaction. We have to include the concept of spin orbit interaction with this so that the magic numbers can be explained. Spin orbit interaction. So this is the concept that we have now, and we are going to start with this concept to understand this. This is very, very important.